So you may well ask, how do I include gravity when considering the mechanics of fluids? I'll demonstrate this by thinking of a fluid blob, as we have done before. So here's a fluid blob, and I'm going to consider the forces and the acceleration of this fluid blob. So first of all, if the fluid blob sits in some pressure gradient grad P, let's say it's a pressure gradient that is high to the top right, low to the bottom left, then grad P points towards the high pressure, and you end up with a force on the fluid blob due to the gradient of pressure that's in the opposite direction to grad P. So in terms of Euler's equation, we get the mass per unit volume, which is rho, times the acceleration of the fluid blob, dv by dt, material dv by dt, is equal to minus grad P. Now we want to include the gravitational force on the fluid blob. The gravitational force obviously acts downwards, and it has magnitude per unit volume of rho g. Of course, we need a direction now, and if I define a coordinate z pointing straight up, I'll have to define it relative to some datum level here. Then I need to multiply that by the unit vector in the z direction, and it needs to be minus that unit vector because it's acting in the opposite direction to the unit vector Ez. Now if we imagine drawing lines of constant z, so here are lines of constant z, then it's quite easy to spot that grad z, this thing here, is just exactly the same thing as Ez. And putting these two things together, we see that the force due to gravity is rho g times minus grad z, and because rho and g are uniform and constant, we get that that's equal to minus grad of rho g z. So let's put that's the force due to gravity, let's put that next to the force due to pressure, and we get that Euler's equation becomes rho dv by dt, that's the mass per unit volume times the acceleration of the blob, is equal to minus grad P minus grad of rho g z. And as a reminder, this is just that the forces on the right hand side are equal to the mass per unit volume times the acceleration of the blob. Now these two terms on the right hand side are just the gradient of two functions, so they can be written as minus grad of P plus rho g z. And on the left hand side we have rho dv by dt as before. Often what we do now is divide through by rho, and we get that the acceleration of the fluid blob dv by dt is equal to minus grad of P upon rho plus gz, where z is the coordinate in the z direction, the vertical direction. Now this is quite a profound result. If, for example, we get that if we say that the velocity is equal to 0, so if the whole thing is static, that implies that P upon rho plus gz is equal to a constant, or it's uniform everywhere in space, and that's the basis of hydrostatics. But the more profound and general result is that this expression on the right hand side here is rather like a new expression for the pressure. It's a combination of the pressure and the gravitational field, and what this is saying is that gravity simply modifies the pressure distribution in the fluid. So when we speak about ignoring gravity, what we often mean is that we can make a separate allowance of gravity simply by subtracting gz from the pressure field.